In the next 3 examples, I will demonstrate the different operating modes of a synchronous generator. These are Isolated Operation Mode, Part 1. Operation Connected to a Network, Part 2. Operation with Fixed Speed, Part 3. Example, isolated operation of a synchronous generator. The schematic shows a synchronous generator rated at 400 megawatts and 20 kV with a round rotor, a transformer from 20 kilovolts to 400 kV, and a switch that connects the generator to the unloaded network at 1 second. A load ramps from 0 to 50 megawatts between 2 seconds and 5 seconds. An AVR, automatic voltage regulator, switches on at 6 seconds, and a speed controller, governor, is active for the entire simulation. The generator's main excitation field is supplied with a high voltage ramp during the first second, from 600 volts to 1400 volts and back to 600 volts in order to quickly reach nominal voltage. The AVR measures on the high voltage side with a target voltage of 400 kilovolts. The speed controller has a set point of 1500 RPM and remains active throughout the simulation. Its switch is set to 500 seconds. All external controllers are implemented as simple PI controllers to illustrate the basic behavior of a controlled synchronous machine. Their dynamics are intentionally fast to reduce simulation time. Notes on the AVR switching logic. The AVR switch must close shortly before the fixed field voltage switch opens. The magnetic field voltage must never drop to 0 because the terminal voltage of the machine would also collapse. Since the AVR supplies high currents, the switch's on resistance must be very low to prevent the field voltage from dropping. The torque control switches are less critical. The electromagnetic torque may be 0 for a short time because the turbine and generator have a large inertia defined by the machine's J parameter, so the speed cannot suddenly fall to 0. Simulation start. The machine starts from 0 voltage. To quickly reach nominal voltage, the AVR is initially set to 1400 volts. The stator copper resistance parameter RCU is set to a relatively high value of 0.01 to accelerate voltage buildup for faster simulation. Voltage behavior. After 1 second, the nominal voltages of 400 kV network and 20 kV generator are reached due to the initially high AVR setting. When the load ramps from 0 to 50 megawatt between 2 seconds and 5 seconds, the current increases and the generator voltage drops slightly from 400 kV to about 397 kV. At 6 seconds, the AVR activates and quickly restores the bus voltage to 400 kV. In isolated mode, a change in voltage directly affects the generator's active power output because the load power depends on voltage. In grid-connected mode, the voltage is more stable, so active power does not change in this way. Speed behavior. During the load ramp, the speed falls below 1500 RPM. Once the final load value is reached, the speed returns to 1500 RPM. When the AVR switches on, the frequency briefly decreases because the rising voltage increases the load current, which increases torque demand. After the voltage stabilizes, the speed also stabilizes at 1500 RPM. Load angle behavior. The load angle increases during the load ramp and then stabilizes at about 12 degrees. Load step of 30 megawatt. A 30 megawatt load step is introduced by setting Vfact equals 3 at 2 seconds and adding a switch at 3 seconds. The load angle changes significantly and the speed shows transient behavior. Additional load steps at 5 seconds and 7 seconds cause further changes in frequency and load angle. The generator output jumps from 30 megawatts to 60 megawatts to 90 megawatts with a maximum load angle of about 21 degrees. Salient pole machine comparison. Setting Schenkel pole factor 0.5 and KC 0.8 models a salient pole machine. After restarting the simulation, the load angle is only about 7 degrees compared to 21 degrees for the round rotor machine. Reactive power in isolated mode. Unlike a grid-connected generator, an isolated generator cannot change reactive power output by adjusting field voltage. Both active and reactive power are determined solely by the load. The field voltage only influences the terminal voltage. If the load is a constant power load, the AVR has no influence on active power. Switching off loads. Loads 1, 2, and 3 are switched off at 9 seconds, 11 seconds, and 13 seconds. The load angle decreases accordingly. After the final load is removed, the frequency takes a long time to settle back to 50 Hz because only friction torque slows the generator. Nominal frequency is reached after about 3.5 seconds. When load is removed, frequency overshoots above nominal, the opposite of what happens during positive load steps. Unit conversion for plots. To display values in correct units, load angle in degrees multiply by 1 degree or 1 volt. Frequency in hertz multiply by 1 hertz, 1 volt. Active power in watts multiply by 1 watt per 1 volt. Synchronizing a second generator. A second generator is added on the right side, including its speed controller, but without an AVR. Simulation end time is set to 30 seconds. Load 3 switches at 20 seconds to show a load step after synchronization. Generator 2 is connected at 12 seconds. Its speed controller stops at 12 seconds and constant torque begins at 12.1 seconds. A ramp from 0 to 20 megawatts between 14 seconds and 18 seconds defines its active power output. Synchronization conditions. At around 9.8 to 10.2 seconds, the generator and network voltages have nearly the same magnitude, and generator 2 leads slightly in phase. To correct this, the speed controller set point can be adjusted to 1500 RPM minus 20 MHz, 49.98 Hz. At 12 seconds, both voltages are in phase, and synchronization is successful. Power sharing. Generator 2 delivers 20 megawatts, so generator 1 reduces its output to 40 megawatts. A subsequent 30 megawatt load step is supplied entirely by generator 1 because generator 2 has no active speed controller. Final outputs. Gen 1 delivers 70 megawatts and Gen 2 delivers 20 megawatts. Generator 2 shows larger frequency transients because there is no speed controller present. Conclusion. A synchronous generator operating in isolated mode requires voltage and speed control. The voltage in the island grid is highly dependent on the load. After the second generator has synchronized, the second generator must not have voltage or speed control. Active power is delivered here via an appropriate torque on the generator shaft. This completes the example. The next example will show a generator interacting with a network with fixed voltage sources, demonstrating active and reactive power behavior and stalling torque at high loads. The following example will show a synchronous generator operating at fixed speed, including one-phase and three-phase short-circuit faults.